One of the most famous theorems in maths is that quintic equations are not solvable, or more precisely, some quintic equations have roots that cannot be expressed in terms of radicals, i.e., finite combinations of all these operations and nth roots. But how do mathematicians even start to prove this theorem? In algebra, we have the concept of fields. For the purpose of the video, a field is a set of numbers where you can add, subtract, multiply, divide, and still end up in the same set. Of course, you can't divide by 0, but you can do everything else. This means that, for example, the set of rational numbers form a field. You can add, subtract, multiply, and divide any two rationals and still end up being a rational. We denote this field as boldface Q. However, this is not quite what we want. Fields don't offer the nth root operation. No worries, we can just extend them. For example, we have the field of rationals here. But as we know, root 2 is not rational, so it's not here. But we can just add it to our field. However, now this is not a field anymore because 1 is here, so we expect 1 plus root 2 to be in it, or negative 1/2 is here, so we expect negative 1/2 square root of 2 to be in it as well. Well, why not add all those into it? This means we want all numbers like a plus b root 2, ab being rational. This newly extended field is denoted Q adjoint square root of 2, the smallest field containing both Q, the rationals, and root 2. I will leave you to check that this is everything in the field. In particular, dividing two such numbers would yield another number of this form. But there is nothing special about root 2. Why not adjoint fifth root of 23, and after that, we can adjoint the cube root of 1 plus 2 fifth root of 23 and so on. As long as you are adjoining the nth root of something we previously saw before, you are fine. Like here, 23 is in Q, and 1 plus 2 fifth root of 23 is in the previous field. This kind of field extension is called a radical extension. But how are they related to solving equations? Well, if the roots can be expressed with radicals, then even if they are this horrendous mess, we can still first adjoin root 89, and then the crazy 23rd root, and then the fifth root, and this whole expression will be contained in our largest field. So if the equation is solvable, then we should be able to find a tower of radical extensions, and the top of the tower contains all our roots. For discussion afterwards, we want to rephrase this slightly. Rather than this containing all the roots of f, the quintic polynomial that we want to solve the roots of, we create yet another field adjoining all the roots of f to q, which is called the splitting field of f. The top of the tower containing all these alphas means that it contains the whole splitting field, and of course the splitting field contains Q as well, so this creates another side tower of extensions. This is the full setup of the question. Even though it looks more complicated, it is more systematic, allowing us to progress, but still, it has exactly the same meaning as we set out for. However, a word of warning ahead. While I try to make this as accessible as possible, do notice that typically at least 2 semesters worth of courses are needed as prerequisites before you can go to a Galois theory course, which is the kind of stuff we are dealing with here. So I have to strip away a lot of details. Luckily, all of them will not affect the core understanding of what's really going on. So hang tight. Things will get a bit more difficult from now on, and may need a second or maybe third viewing, but I promise it will be worth it. We need to introduce another big word here, automorphisms. Auto means to itself, and morphism refers to structure-preserving maps. In the context of this video, it means a function from a field L to itself fulfilling some properties, namely, preserving algebraic relations. This means that applying sigma to the whole expression is the same as applying sigma individually to x and y. Same for the other operations. Another important property is that sigma keeps x unchanged if x is inside a smaller field K. This K is established from context if we are considering the field extension from the smaller field K to the larger field L. And finally, this sigma has to be a one-to-one function. Don't worry if all these sound gibberish, because there will be an example that will feel familiar. Yes, complex conjugation. You can check that complex numbers do form a field, and that applying it to all the real numbers will not change anything. Then you can check one by one that conjugation does preserve all these algebraic relations. And of course, this is a one-to-one function, because after all, conjugation only changes the sign of the imaginary part, and so is easily reversible. So considering all these, if we are thinking of the extension from the reals to the complex numbers, then conjugation is an automorphism. But there is another, perhaps easier way of thinking about automorphisms. Rather than this general field extension from K to L, we consider a special case when L is a splitting field of some polynomial over K. What this means is that we have the polynomial f, and all those coefficients come from the small field K. Finally, L being the splitting field means that we adjoin the small field K with all the roots of f. Now, in this particular case, what can we say about the automorphisms? Well, L is constructed from the roots of a polynomial, so by definition, if we plug in a root alpha to the polynomial, we should get 0. But what if we try to apply sigma to the whole equation? What would that do? For the left-hand side, applying sigma to 0 gives 0, because you can express 0 as alpha minus alpha, which then, by the automorphism properties, we can distribute the sigma, and so we end up with 0. Okay, now onto the right-hand side. Let's focus on this term. We can use the distribution properties of sigma on products to arrive at sigma of an times sigma of alpha to the n. However, an as a coefficient of the polynomial comes from k, and so sigma should leave it unchanged, which means we get an times sigma of alpha to the n, which is our first term in the final equation. But with exactly the same argument, we will get this equation involving sigma of alpha. But now compare these two equations. What's the difference between them? The only difference is that alpha is now changed to sigma of alpha. And this means that sigma of alpha is just another root of the original polynomial f. This has huge implications. If the polynomial f has all these roots, and we also assume that it has no repeated roots, which is also the assumption for all polynomials throughout the video, then what sigma does is to move the roots to some other roots. But at the same time, because L is just formed by adjoining K with all these roots, everything in L can be expressed in terms of K and all the roots. Given how the automorphism sigma preserve algebraic relations, sigma of anything in L can be expressed in terms of K and sigma of the roots. So if we know what sigma of alpha 1 up to alpha n is, then we know what sigma of anything in L would be. In other words, sigma of the roots define sigma of everything. This is to say that automorphisms really are just permuting the roots, nothing more. Of course, this nice interpretation of automorphisms only works if L is a splitting field of some polynomial f over k. In this case, the field extension from k to L has a special name, a Galois extension. To be absolutely clear, the field extension is Galois if L is formed by adjoining all the roots of a polynomial over k. Also, we want to collect all these automorphisms together. This collection of automorphisms is usually denoted aut L over K, aut meaning automorphisms, and L over K represents our field extension. This collection of automorphisms is called the Galois group of the extension. In this case, a group means that doing some permutation of the roots, then do another permutation, is just another permutation, and also that if this is a valid permutation in the Galois group, then reversing it is also another automorphism in the group. So to recap, when you have a field extension, with L being the splitting field of some polynomial f over k, then we call it a Galois extension. On the other hand, we have the Galois group of this extension, which contains all valid permutations of the roots of the polynomial f. I know this all sounds abstract, so we are going to see two important examples now. First, we will consider this polynomial. If we use complex numbers, we can locate where the roots of this equation are, evenly distributed across the unit circle. They are 1 and powers of zeta, zeta being the first root along the circle. Now that we know the roots, do we know something about the Galois group? More precisely, we will be considering the extension from Q to the splitting field of f. Even though I said we need to adjoin all the roots of the polynomial, just in this case, the other roots are powers of zeta, so adjoining just zeta would be enough, saving some space. But what would be the possible automorphisms in this case? One actually needs to remain unchanged because it is in Q, but zeta can go to any other root except 1 because 1 is already taken. Let's say, for example, zeta goes to zeta cubed. Then what? By definition of automorphisms, if we apply an automorphism to zeta squared, then we have sigma of zeta whole squared. In this case, zeta has gone to zeta cubed, and so zeta squared needs to go to zeta to the 6. But because zeta, as illustrated, is a fifth root of unity, zeta to the 6 is just zeta, and so zeta squared goes to zeta. Using the same exact argument, we can find out where the other roots go, and of course, 1 remains unchanged. However, the main observation is that once you know where your automorphism sends zeta to, then you know where everyone else goes, and of course 1 still remains unchanged. This means that we can label this automorphism as sigma 3, which literally just means sending zeta to zeta cubed. And of course, we can generalize. Label sigma L as the automorphism sending zeta to the L. However, there is one very important property about this Galois group. If we consider doing sigma M, then sigma L, what would that give us? Well, doing sigma M would give us zeta to the M, and then by the definition of automorphisms, we take the power out, and finally we get zeta to the Lm. But why do we want to find out what two automorphisms do to zeta? Well, using the same argument, applying the automorphisms the other way around yields the same result. This turns out to be a special property that only some Galois group will have. This kind of group is called abelian. To be absolutely clear, abelian Galois group is when swapping the order of automorphisms yields the same result. So the Galois group, where we consider this polynomial x to the n minus 1, is abelian. Let's look at another example. Instead of 1, we look at nth roots of theta. Again, if we plot the roots on a complex plane, they will form a circle, just not necessarily a unit circle. If one of the roots is alpha, then the other roots are alpha zeta squared, and so on, multiplying alpha by an nth root of unity. However, unlike in the previous example, we will not start from Q. Instead, we start with a field K, and this field contains the nth root of unity. It doesn't have to be, but it will make the discussion way easier. This also means that the theta comes from K. Anyway, the field extension here is again to the splitting field, adjoining all the roots. However, this time we only need to adjoin alpha, because the roots are all made up of alpha and zeta, and we already have zeta in K, so we just need to add in alpha. Just like before, we will investigate the Galois group of this extension. For this, we ask where will alpha go? It can, for example, go to alpha zeta squared, and similar to before, we will denote this as sigma 2. Okay, but where will alpha zeta go? Well, according to the preservation of algebraic properties, we get this. However, zeta is in the original field K, and so sigma 2 leaves that unchanged. On the other hand, by definition, sigma 2 sends alpha to alpha zeta squared, and so we end up with alpha zeta cubed. Quite similarly, we can already tell where all the other roots are going to go. So again, we can label the automorphism by sigma L, indicated by where it sends alpha to. Very similarly, we want to see what two automorphisms do to alpha. Again, we do the inner automorphism first, giving us alpha zeta dm. Since zeta is originally in our field K, this part remains unchanged, and we finally have alpha zeta to the L plus m. Although this is slightly different from last time, we still have that swapping the order of sigma L and sigma m doesn't matter. So again, the Galois group in this case is still abelian. One thing I want to point out is that since the automorphism is already determined by where alpha goes, it rules out a lot of permutations. The only automorphism sending alpha to alpha zeta squared permutes the roots like a star shape, so this is not possible. Yes, it is still a permutation of the roots, but no automorphism looks like this, and so this permutation is not in the Galois group. So in some sense, you can intuitively think of the Galois group as a measure of how related the roots are. In this case, the roots are very related to each other. They are just different by some powers of zeta, so there aren't many available automorphisms, and the Galois group remains very small. But the main message here is that in these two examples, the Galois groups are both abelian. Do notice that we did make sure that zeta was in the starting field in the first place for all these to make sense. This is called a Kummer extension, adjoining nth root of something while the nth roots of unity are already there. And this is called a cyclotomic extension, adjoining just nth roots of unity. However, you might be wondering this. If we start from Q and try to extend to Q adjoin zeta, we called that a cyclotomic extension, but because the field has roots of unity there, we can do the other type of extension, adjoining an nth root, or just as we called it, a Kummer extension. But what if we consider the field extension from Q directly to the largest field? The largest field would still be a splitting field of the same f if that theta is in Q in the first place. So this big extension would still be Galois, and we can talk about the Galois group of this extension. Just to be clear, both of these extensions are still Galois extensions, just that they are of special types. The big question here is, are there any relationships between these three Galois groups? That is what we are going to do in the next chapter. Even more generally, when we have such a tower of field extensions where all three extensions are Galois, what can we say about the Galois groups? For now, we want to see the relationship between these two first. The Galois group contains the automorphisms of the biggest field M that leaves all of L unchanged. But of course, if we leave all of L unchanged, K would also not change because K is a smaller field. On the other hand, the other Galois group contains automorphisms of M leaving K unchanged. Since leaving L unchanged implies leaving K unchanged, this means that everything in this group of automorphisms will appear in the other Galois group. In other words, one Galois group is a subgroup of another. But actually, because L over K is a Galois extension, we can say something more. Remember how we said automorphisms just permute the roots? Well, actually, for this argument to really work, L doesn't even need to be a splitting field of F. The only implicit assumption here is that alpha is in L, so that you can apply sigma to it. So L can actually be an even bigger field, it just needs to contain all the roots of F, but maybe something more. In that case, it will still send a root of F to another root of F. So back to this tower of field extensions, and let's say that L is the splitting field of F over K. From what we have just said, the automorphisms of a bigger field M fixing K will still send a root of F to another root of F. However, L is formed by just adjoining K with all the roots of F, and the roots just permute themselves under such an automorphism, so if you start with something in L, you will still end up in L. So yes, even though these automorphisms only fix the small field K but not L, they still send something in L to another thing in L. We now take something random here, say G, and then another random automorphism N from this subgroup. Then consider this rather bizarre combination acting on an element of L. Firstly, acting G inverse on little l would still result in something in L, because that's what we just said a minute ago. Next up, we have N of something in L, and by definition of N, it leaves any element of L unchanged, so it is as if the action of N never happened. But that means we have G inverse of L, which is just L. This means that this weird combination of automorphisms actually leaves every element of L unchanged, so it is just another element in this Galois group. So this Galois group fixing L is not only a subgroup of the Galois group fixing K, but also satisfying this property that G and G inverse just returns something in that subgroup. This kind of relationship is called a normal subgroup. For this reason and ease of notation, we label this Galois group N, and similarly, the other Galois group is labeled G. The relationship of normal subgroups is usually denoted using a little triangle. All these just mean this combination lands us back onto N. Turns out this combination isn't weird or made up, it has some intuitive meaning as we will see later. Okay, so now we established the relationship between G and N, but what about the remaining Galois group? Let's call this Galois group H for easier reference. The elements are automorphisms of L, and here is the insightful idea. An automorphism of M looks something like this, sending elements of M to itself. However, as noted before, such an automorphism would also send elements of L to itself. So if we focus on what G does in L, it looks exactly like an automorphism of L. But because we have restricted our attention to L, it is possible to have another automorphism that does exactly the same thing here in L, but completely different outside of it, so that overall, these two automorphisms are really different, but for our purposes, focusing on L, they are the same. Or Think about it this way. The automorphisms of L are like different buckets, and automorphisms of the bigger field M are like different balls, and we just put the balls in the bucket. Two balls will be put in the same bucket if they agree on the smaller field L. Yet another way to think about this is that if two automorphisms G1 and G2 fall into the same bucket, we can consider the automorphism G1 inverse G2, which can be thought of as the difference between G1 and G2. How different are these two automorphisms? Well, if they are in the same bucket, then by definition, both G1 and G2 do the same thing in L. Now, this combination of automorphisms tells you to do G2 first, which essentially means going from left to right in this diagram, and then we do G1 inverse, which means going back from right to left. So if we apply this combination to any element in L, it would just do nothing. Of course, outside of L we don't know, but at least inside L, it leaves everything unchanged. This is to say that this combination is an automorphism of M, leaving all elements of L unchanged. Or using the lingo before, G1 inverse G2 is actually inside N. In other words, this Galois group H can be thought of as a bunch of buckets containing balls from the big group G, with two balls being in the same bucket if their difference is in the smaller group N. This kind of group is usually denoted as G mod N, a quotient group. So to sum up, we have this schematic diagram with all these three Galois extensions, realizing that N is a normal subgroup of G in the sense that this combination of automorphisms from G and N would produce another element of N. The other Galois group can be thought of as G put into buckets, with two balls put in the same bucket if they differ by an element of N. But how do all these tie to our original question in mind? Finally, we can go back to the problem of solving quintic equations and apply what we know from the last 3 chapters. After all, there are so many field extensions here. Just a caveat though, in order to use what we know, we need all the field extensions to be Galois, so that we can properly talk about the Galois groups. But some of these extensions just might not be Galois. The simplest counterexample would be the field extension from Q to Q adjoint cube root of 2. Sure, this is a radical extension, but we have only added one root of this cubic polynomial into the field. There are other roots involving the cube roots of unity that aren't in Q adjoint cube root of 2, and in fact, this field extension is not Galois. It would be Galois if we also added the cube roots of unity though, but then this will not be a purely radical extension. The solution to this would be to add an intermediate field of Q adjoint zeta. Then, at every stage, we are doing a Galois extension. We first add all the roots of unity, then add all the cube roots of 2. And at the same time, because we are adding cube roots of something at each stage, these are radical extensions. So sometimes we might want to add something more and/or adding an intermediate field so that at each stage the extension is Galois and also radical. We want the extensions to be Galois so that we can apply the tower of extensions we saw before. And we want the extensions to be radical, and more specifically, cyclotomic and Kummer extensions, because that allows us to apply an earlier result that the Galois groups for both types of extensions are abelian. So it is desirable to add even more things into the mix just so we can apply our previous results, which is what we will do to this radical tower of extensions. Well, similarly, we are going to add the roots of unity, where those ni are the orders of the radicals of beta I. This will make all these extensions either Kummer or cyclotomic, and so they're all Galois. But rather demandingly, we also want the big extension from Q directly to the biggest field Galois. The details on how to do it are unfortunately something I want to skip over in this video, but this really doesn't affect the core understanding of what's going on. In any case, we can add enough things so that each of these little extensions are Galois, more specifically, either Kummer or cyclotomic. And this big one is also Galois, which means that the biggest field is the splitting field of some polynomial f with rational coefficients. But the coefficients being in Q means they are also in all intermediate fields, and so all the extensions from any intermediate field to the biggest field are also Galois. And yes, that includes going from the splitting field of our quintic polynomial to the biggest field. And of course, by our definition, from Q to the splitting field is also a Galois extension. So there are a lot of Galois extensions happening. Because of all these Galois extensions, we can associate the Galois groups to each of them. And now we can finally apply all the results we have just seen. For example, the relationship between the Galois groups in this tower of extensions. Let's focus on this main tower of radical extensions, and more specifically, on these three field extensions. From what we saw before, G1 is a normal subgroup of G, and the small extension has the Galois group being a quotient group, the bucket analogy we saw before. However, by construction, we know that this extension is either Kummer or cyclotomic, and so this will have an abelian Galois group, or any two automorphisms here will commute with each other. This means that the quotient group needs to be abelian. Exactly the same argument will also apply here. This means that G2 will be a normal subgroup of G1, and the quotient group G1 mod G2 will be abelian. This argument extends until we hit the last extension, which will have Galois group GR, and similarly, GR needs to be abelian. So putting everything together, we have a chain of normal subgroups, and in each of these normal relationships, we have the quotient group to be abelian. And the final smallest subgroup GR must also be abelian. This kind of relationship has a particular name, solvable. If we can even find those normal subgroups in the first place, then the biggest group here, G, is called solvable. Okay, so the Galois group from Q to the biggest field is solvable, but now we want to focus on the other part of the extension tower. Again, we have that N is a normal subgroup of G, and H can be thought of as G mod N, the bucket quotient group. It turns out that because G will be solvable, we automatically have G mod N to be solvable. I won't really show the full reason of why that is the case, but the main idea is that G being solvable means there is such a chain of normal subgroups, and if we want to show that the quotient group is solvable, we will have to somehow demonstrate a similar chain of normal subgroups. This is done by the put in bucket operation. But anyway, the upshot here is that we can narrow down our focus to just the field extension from Q to the splitting field of our quintic polynomial, which has a solvable Galois group. And here's the catch. The Galois group right here is determined by our quintic polynomial because we are adding the roots of it in this field extension. So our goal here is to find a quintic f such that the Galois group is not solvable, because what we have done here is that if f is solvable by radicals, then we will have this radical tower, which in turn means that the Galois group generated will be solvable. So if the Galois group is not solvable, there is no way that the polynomial is solvable by radicals, and we are done. So we need to demonstrate that sometimes the Galois group can be not solvable. However, When I planned this video, all proofs I could find are either too computational or just fiddling things around and somehow magically everything works out, not giving much insight. So rather than giving the exact rigorous proof of why a Galois group is not solvable, I will appeal slightly more to intuition instead. If you really want to know the full proof, do go ahead to the links in the description. First, recall what we really mean by a normal subgroup of G. We said that if we pick a random element in N and another random element in the larger group G, then this weird combination would still be in the smaller group N. But it is also important to remind ourselves that this is a group, which means that composing two automorphisms in N gives you something in N as well, and reversing the automorphism gives you another permutation in N, and applying these two properties, we get that the identity do-nothing permutation is also in N because it is just doing any automorphism N, then undoing it. These conditions for N turn out to be really restrictive, so restrictive that for the group we are considering, there is basically only one interesting possibility. The Galois group we will be considering includes all possible permutations of the 5 roots. This is called the symmetric group of order 5, usually denoted as S5. As we have said just now, any normal subgroup needs to fulfill all these properties, but let's focus on this particular property. What does it really mean? Let's suppose that the automorphism N sends a root x to another root y, and then G will send x and y to g of x and g of y respectively. So this weird combination asks us to first reverse the action of G, so if we first start with g of x, then G inverse sends it back to x. Then N will send x to y, and finally G will send y to g of y. So the overall effect of this combination of automorphisms will send g of x to g of y. So this combination, also called a conjugate of N by G, is actually very similar to N itself. It's just that we need to relabel x and y as g of x and g of y respectively. For example, for such a Galois group S5, if we say an automorphism N permutes the roots like this, what we call a 5 cycle, and G is just swapping these two roots around, leaving others unchanged, then what is G and G inverse doing? Well, for this purple arrow at the top, its destination is the blue root, but under G, the blue root goes to the red root, and so this purple arrow will be transformed as such. Similarly, this red arrow on the right starts from the red root, but again, under G, the red root goes to the blue one, and so the red arrow will be transformed as such. Finally, we get to the blue arrow. Again, G just swaps the two roots, and so it just reverses direction. And note that now G and G inverse is still a 5 cycle. In general, if we pick some other G in our Galois group, then we can obtain any 5 cycle. But that's only talking about one of the properties of the normal subgroup. What we have demonstrated is that if we let one 5 cycle into N, we have to let all 5 cycles in just by this conjugation property. But we still have the group property that composing two automorphisms gives you another automorphism in N. So if, for example, composing two 5 cycles gives you a 3 cycle, then we have to admit a 3 cycle, which then means we have to admit all 3 cycles in, and so on. So one 5 cycle already causes quite a bit of chaos. We need to let so many things in because of it, and sometimes the whole group needs to be in as a result, so there aren't many such normal subgroups. As if that's not enough constraints, remember that a solvable group also requires that the quotient bucket group needs to be abelian, with the final smallest group abelian. So a solvable group should be relatively rare considering all these constraints. So it should not come as a surprise that S5 is not solvable. It is ridiculously difficult to be a solvable group. Instead, it should come as a surprise that S4, S3, or S2 are solvable groups. The main reason is that in this conjugation property of the normal subgroups, if we have a smaller group containing fewer permutations, then we don't need to conjugate our n by so many permutations g, which results in fewer constraints due to this property. I know this might not be satisfying to some, but ultimately, when you try to dissect the proof that the symmetric groups of orders 5 and above are not solvable, it does ultimately boil down to the constraints being too strict. So that's the ultimate reason why S5 and indeed S6 or above are not solvable. So what? Remember that throughout the video, we established that if the equation is solvable by radicals, then the corresponding Galois group is solvable. We have demonstrated, at least intuitively, that S5 is not solvable. But is there even a polynomial with Galois group S5? If such a polynomial exists, then it is impossible to be solved by radicals, otherwise the Galois group would have been solvable. We again appeal to intuition. Remember that previously we said that the Galois group is a measure of how related the roots are. In this Kummer extension, the roots are made up of only alpha and powers of zeta, and they are very algebraically related, and so there are lots of restrictions on the automorphisms, making the Galois group very small. In fact, there are only 5 automorphisms in this case. But the Galois group we are considering allows all permutations, the opposite of what we had, which means that the roots are very unrelated to each other. That should be the majority of cases. After all, if we randomly pick a quintic polynomial, there is no reason to expect their roots are related. Indeed, I just randomly wrote down all these polynomials and then checked with the computer. They all have Galois group S5. However, even though in some sense almost all polynomials have Galois group S5, proving that, for example, x to the power 5 minus 6x plus 3 has this Galois group isn't easy, though this is probably the simplest to justify. Again, there will be links in the description for those who know a little bit more about group theory and you want to know exactly why this has Galois group S5. But still, the fact that most polynomials have Galois group S5 means that most quintics are not solvable, simply because the roots are not very related. Given how complicated this whole thing is, it's entirely normal to feel a bit lost, so here is an overarching summary of what we have just done. We first rephrased solving by radicals using the language of field extensions, but this is a difficult problem because even the smallest field Q, the rationals, is still infinite. So we spend a lot of time trying to transform it into a problem about Galois groups, because Galois groups are permutations of the roots. When there are only finitely many roots, there are only finitely many permutations, so Galois groups are finite, which is infinitely better to handle than fields. So because of this transformation of the problem, we only need to focus on the groups. Finally, we used intuition to realize that most likely the Galois group is not solvable. In other words, we have rephrased it into a hard problem using fields, then we transform it into an easier finite problem about groups using Galois groups. And then we focus on solving that easier problem. At least for the last part, if you want to know about that proof in more detail, you will need quite a bit of group theory, which I have a few videos on the channel. I hope this makes you more motivated to study more about group theory. In any case, thanks to the patrons for your support, and as always, subscribe with notifications on, like, comment, and share the video. We are so close to that 100,000 mark. See you next time.